Okay. Hi, everyone. I guess we can get started. So thank you for joining this session. Thanks AnyLogic for inviting us to present our work here. So today we are going to share the ModelOps simulation tool, which is to observe the value and impact of the ModelOps practices and infrastructure. Okay, firstly, I'll introduce the team. So here we have Hannah and me, and both of us are senior data scientists from PwC. For today's agenda, firstly, I will do the intro and the solution motivation, and then Hannah will have a detailed introduction of our solution. And after that, we have a demo of our tool. So let's get started. First part is a background introduction. So some of you may hear about ModelOps. So what is it? ModelOps is fairly a new discipline that addresses the governance and the lifecycle management of a portfolio of AI or machine learning model, and it's often used to capture the opportunities for improved value, quality, and efficiency. It includes activities and capabilities such as initial model deployment, ongoing automated monitoring, evaluation and performance check-ins, and continuous retraining and redeployment. In the life cycle of a model, the business value is changing all the time. So currently, more and more organizations are relied on the portfolio of advanced model for decision making, but a few of them are implementing model ops practices, which results in some missed opportunities at every stage of the model lifecycle. Like we can see from the chart below, so before the model is deployed, there is a time period for model development. For this whole time period, the business value is always negative because it didn't generate any value for the company or something. So that is we call the missed opportunity. So once the model is deployed, in the beginning, the value will increasing, but if we don't have some maintenance or if we don't have like a monitoring, the value will decay as time goes. So that is why we need a model ops, because model ops can capture more value faster and can also prevent the missed opportunities and the value decay. This is also the reason we build the solution, because like we see here on the left side, those are the challenges the company we are facing. So we want to demonstrate the value of model ops practices for our clients. Then we use simulation. That is because simulation allows us to reflect the complex dynamics and also can visualize the model portfolio in an appealing and easily understandable way, and it can also demonstrate the value and the cost of implementing various model ops capabilities separately or in combination. And it can quantify outcomes by incorporating real client data. And lastly, it can help our clients to test and experiment with different probabilities as a decision-making tool. And now let's move to our solution. So our solution includes four key components. First of all, we have like a process flow to describe the typical life cycle of our AI or machine learning model. And for each model, we represent it as an agent in our simulation, and it has a state chart to track the operational status. And for the usage dynamics part, we have like a bus diffusion model to realistically represent the interplay of model performance, user adoption, and the usage volume. And in this tool, we demonstrated five capabilities of model ops, and each of those was represented as a stock and a flow, allows us to model various levels of investment and maturity. Okay, next I move to Hannah, and she will do a brief introduction of each of our solution. Hannah, next to you.
Thanks, Jingshu. So Jingshu just gave us an overview of the components in the solution. I'm going to talk in detail about each one. So first we have the process flow that lets us reflect a typical model lifecycle. This is a pretty standard lifecycle. We have an idea backlog. The models get built and deployed by developers. Then they live in production for a while, and eventually they retire or they become obsolete. And the main part that we're interested in is their activities while they're in production, and they can either be online serving predictions, or they might be offline with an issue or doing regular retraining. So Another part of this, what we want to reflect in a realistic way, is the development team. So we have developers who are resources within the model, and we allow them to have prioritized activities just as they would in a real life situation. So their number one focus is always the models that are already in production. Their first priority will to be repair any issues that come up with the models and take them offline. We always want to prioritize having our models online and operational. The second priority is to do the regular retraining. So every model has a schedule on which we expect it to need retraining. Priority number 3 and 4 is then to deploy new models or build entirely new models. And those are lower priority activities. Again, we're focusing on the models that are in production. But when the developers have capacity, we do allow them to build and deploy additional models. So the next piece of the next component is the models themselves. So within this simulation, each model is an agent. Each machine learning model is an agent. I realize we're using the word model in a lot of ways. So the ML or AI models that are in the portfolio, each one is its own agent, and we have a state chart that controls the detail of the activity that the model is involved in at the moment. So once it enters production, hopefully it's spending the most of its time online where it can make predictions. In most cases, its scheduled retraining is happening on a periodic basis, and that doesn't necessarily take it offline. There's 2 real scenarios where it can go offline in our simulation. One is when an issue comes up. There are various types of issues that can occur in the model, but no matter what happens, the model is going to go offline and it'll be unable to make predictions. Then we need to assign a developer to repair that issue and bring the model back online. The other event that can happen, very specific to our model, is a drift event. So all models experience some performance decay, as Jingshu alluded to in the beginning. And if we aren't addressing that, it can become so severe that the model might essentially become useless. And we would then need to take it offline to do some diagnosis or repair or additional retraining that wasn't already covered. So this state chart, we can examine for any individual model and see what it's doing. It also allows us to track statistics about the model, see how long they've been online, how many predictions they've made, the total value and the costs that they've generated. So as Jingshu mentioned, the motivation for this simulation is kind of grounded in business imperatives. We wanted to be able to demonstrate the value and the impact of possibly implementing ModelOps practices. And to understand that, we need the simulation to tell us about the value and the cost that's being generated by the model portfolio. And we use 3 factors to build that total value and cost. One is the user base. So for each model, that's the number of people that use the model per day. We also look at prediction volume, which is the number of predictions per user per day, average prediction volume or request volume, and then the value and the cost per prediction. And this is something you would work with a business user to figure out how would you assign a value to the prediction that the model makes, what kind of cost do you think is associated with serving that prediction. When we aggregate these factors across all the models, then we know the total net value of the model portfolio. So to understand how those 3 components work together, in the simulation demo, there's some under the hood factors that you won't really observe in the same way that you'll be able to observe the process flow. So I want to explain those a little bit more so that you know what's happening kind of under the hood. So the first part is model predictive power. As Jingshu mentioned, the power or the predictive power of a machine learning model decays from day 1. They never perform as well as they do on their first day. And to simulate that, we can add this decay factor that slowly decays or degrades the performance of each model. And that happens according to a cadence that's specific for each model. When that decay starts to occur, it can have a negative impact on all those 3 parts of our business calculation. So this is a very important part of the kind of realistic nature of the model that you just don't observe in the simulation demo. So I want to talk about how it affects each of those parts of our calculation. The user base we're using a BAS diffusion to reflect adoption. So we have a pool of total potential users, and we slowly convert them into current or actual users for each model. So each model has its own BAS diffusion to model its user base. The main thing that's specific to the way ours works is this decay factor. So the same performance decay that's occurring slowly over time for each model is impacting the rate at which people are adopting that model or beginning to use that model based on its effectiveness. Obviously, if the model is performing poorly, people are not going to be interested in using it. And so that adoption rate will drop. Once we understand the user base for each model, and that's being directly affected by the predictive power of the model, then we can understand the total user base and aggregate that up to the total model portfolio. The prediction volume, so this again is the number of predictions that each user is making per day on average, is also affected by that decay factor, and it's affected by a couple other elements of model performance, or really one element combined, which is the proportion of the time that the model is online. So even if the model is performing really well, if it's always broken and rarely online or rarely available in some other way for people to use it, they will probably stop using it. They're not going to rely on it. They'll come back less and less, and they may even abandon or stop using the model completely, in which case their prediction volume is going to 0. We also use the decay factor here. So if the decay is high and the performance has been degraded, again, people are probably going to use it at a lower rate, even if they continue to be a user. So again, we're aggregating this prediction volume for each model and then aggregating up to the total portfolio of models. Within our solution, we're talking about 5 specific ModelOps capabilities, and you will see a few of them demoed in the demo, but not all of them. So I just want to explain what each one is. First is automation. So this is activities around automating parts of the model lifecycle, including model building, deployment, the scheduled retraining or the regular retraining that occurs, and some types of issue detection and resolution. So the more we can automate those activities, the more reliably they would be performed, the more timely fashion they'll be performed, less potential for errors. Automated monitoring is also a very valuable capability that we could implement as part of ModelOps. This is allowing the developers to monitor the performance of the models constantly. So when a drift event starts to occur, or if there's some other kind of performance decay, we can know about it quicker and we can intervene more quickly. And that allows us to keep the model's predictive power high and reduce all those potential snowballing effects of people wanting to use the model less, of the value per prediction falling, et cetera. Lineage and versioning is a kind of specific capability that we implemented, understanding that there are some models that are subject to regulatory and compliance rules or regulations. So there might be a need for an organization to be able to show documentation about a model, maybe some visibility into its lineage, previous versions of the model, maybe some explainability. And having those things available can let you respond more quickly to these requests and decrease the likelihood that your model is going to get taken offline or that you won't be able to use it for some reason. Auto-scaling, pretty self-explanatory. The growth of the usage over time with the model could maybe eventually exceed the capabilities of the infrastructure to serve that volume of predictions. If we implement some auto-scaling capability, that allows us to automatically increase the capacity and capture those additional predictions. And lastly, model rollback. So this is a capability that would allow us to bring a previous image or an older version of the model online while the current version is offline for some reason. So maybe it's getting retrained, maybe it breaks and falls offline. If we can bring another version of it back, even if it's maybe not as good a version or not the latest and greatest, at least there's something available to make those predictions. So each of those capabilities we model also as a stock and flow. This allows us to select a particular level of maturity or investment that we want to simulate. So maybe they want to implement, just kind of an elementary level of automation in their portfolio and see the effects of that, and then model a much higher level of investment and see what the difference is. And then we also use a flow rate to reflect the fact that building this functionality takes some time. So that lets us divert the resources. We take some developers to build that capability, and we take them out for a period of time, depending on that level of maturity. And we also delay the realization of the benefits in a realistic way within the simulation. So now we have a demo. We actually did a video of the demo just to keep it a little tighter. And
ModelOps simulation tool. We're simulating a portfolio of machine learning models and the developers that support them. The objective of the simulation is to show how investment in infrastructure, automation, and other ModelOps practices can improve the performance and the value of the model portfolio. Let's check it out. At the top, we see an overview of the model portfolio with key stats about the models, their operational status, and the value and the cost generated to date by the portfolio. We also see our dev team and their current capacity, and we can add or remove resources as needed. Below the summary, our main process flow describes how models move through the lifecycle. We start out with a few models already in production, and additional models will be pulled from the backlog for development as soon as the dev team has capacity. In the two smaller process flows below that, we can also see details of models that are currently offline, either due to an issue or scheduled retraining. Let's examine the model agent briefly. Here we can see the details of each model, which is an individual agent, and its current status. Models can either be offline or online. Each model has its own cadence of normal scheduled retraining, which doesn't necessarily require it to be taken offline. Models go offline either due to an issue arising or due to a drift event. Drift events occur when the model's performance has decayed so much that it's no longer making good predictions and it needs to be taken offline for diagnosis and repair. Let's head back to the main view. So now we can get a pretty good sense of what's been going on with this portfolio. We can see that the development team is quite highly utilized. They're spending most of their time working on the current portfolio, either fixing issues or retraining models, and less time on developing models, as is their priority set. We can also see that the value and cost are pretty tightly aligned at the moment. Hopefully we see value begin to outpace cost at some point. Online-offline time looks okay, not great. Time to experiment with ModelOps. So we'll start by doing a pretty high level of investment into our monitoring capabilities. The first thing they see is that we're going to be dedicating several of our developers to this monitoring effort, and we'll start to watch the investment ramp up in this chart down here. The benefit of performance monitoring is important for all AI models. All machine learning models experience performance decay from the moment they're deployed into production, and sometimes this decay can be more rapid. For example, if there's an external event that changes the data generation process for what we're trying to predict. If we implement this automated monitoring, we can catch performance degradation much more quickly and intervene before it starts to become a problem for our users, which would decrease the value of our predictions. The main effect we're hoping to see from this monitoring capability is that our portfolio should start generating more value. And eventually, again, we want that value to outpace cost. The reason for this is that we're maintaining models at a higher level of performance, and with more predictive power, they're going to generate more value. So we can see in the chart on the bottom that we've reached just about the full amount of investment and maturity for our monitoring capability, and we can already see that value is beginning to increase and outpace costs that we've incurred to date, even with the cost of actually investing in this capability. So that's great. Next, we'll begin to implement some automation capabilities. We'll go with a slightly lower level of investment here just to see what happens. Several parts of the model lifecycle could be automated, but at this level, we'd be focused on automating the deployment process and also on automating the scheduled retraining for each model. Up at the top, as before, we can see that we've lost a couple of developers to this project, this effort. And again, we'll start to see the investment level ramping up down here at the bottom. The time to complete retraining should come down as we fully reach investment in this capability. The deployment time should also start to come down. And over time, the proportion of time that developers are spending on retraining models is going to shrink in comparison to the time that they spend fixing issues and developing new models. These are all great benefits that we'll start to see over time with the investment into this capability. The last thing we might think about improving is looking at this online-offline time, which is frankly not great. And the capability we could implement to help us out there is called model rollback. So we'll implement the model rollback capability. This is a functionality that lets us revert to an older version of the model while the current version is offline for some reason. Value and prediction power may not be as high for the older version of the model, but at least we have something available. We had one dev that went to work on that, and we ramped up pretty quickly with that capability, as we can see in this chart. And right away, we start to see the impact. So the proportion of time that the models are offline starts to go down dramatically, and it's eventually going to reach 0. I hope this demo has shown the benefits of a simulation approach to understanding ModelOps. This approach can be customized to represent model portfolios of any size and maturity level, and the 5 ModelOps capabilities shown here represent only a small number of the potential functionalities that could be modeled and analyzed.
Great. So that's the conclusion of our presentation, and we have time for some questions. And I see a couple in the chat already. There's a question about how we came up with the 5 ModelOps capabilities that we're modeling here. So we actually worked with a team that specializes in ModelOps within PwC to build this, and they gave us a lot of input on what types of capabilities would be useful to model in a demo. Again, this is a demo. There's no client data in this. So they picked a few things that they typically talk about with clients that they'd want to be able to show. And they gave us some input on how implementing those capabilities might affect the functioning of a model portfolio. We were also asked how we validate and verify the model. So again, this is a demo. It doesn't have any real client data in it, but were we to develop something like this with another organization or maybe with PwC's own internal data, this would be an effort in close collaboration with the business team. So in order for the outputs of this model to be valuable, it'd be really important that the business gives input on how we determine those things. In particular, things like the value and cost generated by the model. So not all organizations are at that level of maturity. And so for those groups where they're not quite sure how to assign that type of value, we might focus on some other things. Like maybe we would focus the visualization a bit more on how the users are adopting the model, what kind of prediction volumes we're seeing, what kind of stickiness people have with the model. And we might focus the simulation a little bit more on that if they're not quite at that level of maturity. We also have a question about integrating machine learning models into AnyLogic. So just to clarify, there are no machine learning models actually running as part of this simulation. Each agent is just a kind of a representation of a model that might be running. So we could give the agents all kinds of characteristics that a machine learning model might have, but we're not actually running any or really using them to make predictions. That's all simulated. There's also a question about the appearance of issues in the model. There's a couple different types of issues. So there's some issues that occur. There's kind of like a daily random chance that an issue will occur for any given model that'll take it offline. And that simulates all the myriad things that can go wrong. Maybe something in the data pipeline breaks or some dependency fails, any reason that could take a model offline. And then there are some specific events that can occur as well. So one example is we can have issues occur with deployment, and those can actually occur at a pretty high rate. So, sometimes up to 50% of the time in the model, when a machine learning model gets deployed, the deployment will fail. And that means that the model will not go online, and that issue has to be repaired. And some of those issues have interplay with the ModelOps capabilities. So implementing automation, for example, can significantly reduce the occurrence of those deployment issues. Another question, some key challenges we face while creating this model. Definitely a challenge is that like I said, this is a demo, so we're not using any kind of real client data here. So coming up with reasonable values for a lot of these things was a challenge. And Jingshu and I both work also on ML models, so we have some sense of that. But it was important for us to be able to have the ModelOps team as a resource to understand how the capabilities that they're working with every day would affect the parts of this that we understand. I don't know, Jingshu, if there's anything you want to add about challenges.
Yeah, I think Hannah covered most of it. And then I want to add one more thing is because we are both data scientists, so we know some process of it. So sometimes we need to think about what will happen during the whole ModelOps process, and we want to include more things or more steps into our simulation model as possible. Yeah, and also sometimes because this is not real data, so we need to after we build the simulation, we run the output. We want to see if the output just come out as what we think. So that's the thing we need to do some a lot of trials.
Great. Another question: any takeaways for internal machine learning ModelOps or DevOps teams in organizations having modeled this? I would say my takeaway was that there's such a huge variety of things that you could be doing. So even in this solution, we're making a lot of assumptions about the maturity level of the organization. So you probably heard us say a lot of times, like the model is online or offline, but in a lot of places that the model isn't online, it's just a collection of machine learning models that are living on data scientists' laptops. And that would be a completely different thing to reflect. So I think the importance of this is that it might sound like a capability that is too advanced or sophisticated for an organization that might not have a lot of maturity in this area, but there's capabilities at kind of every level. So even, there's a lower level, or not a lower level, but an earlier level of MLOps capabilities that we could consider part of this that aren't reflected here. So just even getting models off of people's laptops could be a step. So I think it's important to have an assessment of where the organization is currently. So if you have models living on laptops, you're probably not in a place where you're thinking about, oh, how do I automate, retraining? You probably want to think about some earlier steps before that. Question, is this model shown to clients as part of the ModelOps practice? Yeah, so the purpose of this demo was to create something that the ModelOps team could use as a demo and as a conversation starter and a way to actually show our clients concretely what we're talking about when we discuss these different capabilities. A typical way that they might use it would be to just demonstrate implementing a specific capability on a portfolio. So we tried to make this fairly generic in a way that any organization could kind of see those benefits. Question, how long did it take to complete the demo from start to finish? Jingshu, do you remember how long?
Around 2 months. 2 months. I think so, right? From the beginning, yeah.
Yeah, I think that's about right. Yeah, we had there was a lot of iteration. I think we started with something a lot more basic. So in the beginning, we actually just had a single stock and flow that represented ModelOps capabilities. And then once we had the kind of the guts of the model working, we started to add more of the specifics of the different capabilities. And obviously that increases the complexity because each one has its own very particular impacts on the model portfolio. I see also one question I missed. What's the contrast between ModelOps and DevOps for simulation/ML projects, and what does CI/CD contribute? So the contrast between ModelOps and DevOps, I would say ModelOps is, in my mind, kind of a descendant of DevOps, or it's kind of inspired or shaped by DevOps, but it's very specific to machine learning projects. I'm sorry, there is a utility truck outside in case that noise is getting picked up. So it's very specific to the problems that come up with machine learning models. So these ideas of multiple people maybe collaborating on a model, different people perhaps retraining a model, different parts of the organization maybe wanting to use different versions of a model, models being part of multi-model pipelines, or maybe one model feeding outputs into another model's pipeline. All those things are complexity that come up specifically with machine learning models. And I think it's also important to say that ModelOps is considered a discipline not just for ML models, but you could also use it for simulation models, for any other type of complex decision-making models.
Yeah, this is like a general process. We just want to, it can be applied to any kind of this really similar processes. I think that's all the questions.
I think that's all the questions.
Yeah.
Great. Okay. Hannah, Jingshu, thank you very much for your presentation today. We really appreciate you coming.
Thanks a lot.
Yeah. Thank you.